안녕하세요 여러분, 해리입니다. So in the last video we have finished learning the three forms of complex numbers, and then we have covered all the operations, and lastly very important theorem called the De Morva theorem. So what we are going to do today is that I'm going to explain the two main applications of complex numbers that we can use. And please be aware that we're going to use this a lot. So first we start with roots of complex numbers. So what it means is that we're going to find the complex roots, but not any functions. So the function will be specifically designed, something like so mainly we're going to learn two types. So when we have something like a polynomial equals to 1, so a variable to n equals to 1, so no other term, or a variable to the power n equals to another complex number. So for the case A, the roots we find here are called nth roots of unity, because with the roots, if you plot them in the Argand diagram, you will have a regular polygon. So for example, let's say so I'll give you an example. So let's say we have z cubed equals to 1. So that means, okay, so for this one, we can just directly find what we know. So factor theorem, right? Oops, no, so this is z, right? So we can factorize this cubic equation into z minus 1 and z squared plus z plus 1. Okay? So that means we have roots equals to 1, or using the quadratic formula, this or that. So what I mean by we can draw a regular polygon is that if you plot real with imaginary, so if you plot these three roots in the Argand diagram, so that should be -½ with root 3 over 2 and negative root 3 over 2, and this will be an equilateral triangle, so a regular polygon. Okay, and that means if we find the fourth roots of unity, which means z to the 4 equals to 1, then the roots will form a square, and to the 5, that means pentagon, to the 6, then we'll have a hexagon, and so on. Okay, so for a cubic function, we can use what we know. So we can use factor theorem and then find the other factor. So the other factor would be in quadratics, so we can apply quadratic formula to find the roots. But what if we have like something like degree 4, degree 5, or even degree n? So for this case, I'm going to give you an example. So let's say we want to find the 6 roots of unity, which means that we want to find the roots of this equation. So according to the fundamental theorem of algebra, there must be 6 roots, right? So some of them can be repeated, but we don't know yet. But at least we know that this equation will have at most 6 roots. Okay, so we can, in order to find z, what we can do is that we can let z be x plus iy, and then you can compare it So by using binomial expansion and then letting that equal to 1, and you can possibly find x and y, but we don't want that. So because it's going to be very complicated, you have to make a binomial expansion with degree 6. So what we are going to do is we are going to let z as in polar form. So let's say z equals to r cis theta, then z to the 6 would be r cis theta to the 6, and that will equal to 1, right? And using the theorem that we've learned, this theorem, we can write this as r to 6 times cis 6 theta, right? But what about 1? And this is why I have been emphasizing the importance of these three numbers. So we can write 1 as in cis 0, because what's the modulus? Modulus is 1. Then what about the angle, the argument? It's arctan 0 over 1, right? Arctan 0 over 1, that's 0, right? So we can write this as cis 0. So this is what we will have, right? Then r to the 6, so just compare like this. Then r to the 6 will be 1, and cis 6 theta will be cis 0. Okay, r is either plus and minus 1, but we reject negative 1 because, again, modulus cannot be negative, right? So r equals to 1. Then what about this one? So we can see that the angle 6 theta must equal to 0, right? Then do we just have one value of theta? No, because in that case we will just have one root, right? Then what does that mean? So we, as I said in the beginning, we know that this one has 6 roots, at most 6 roots, right? And we also know that for cosine and sine, their period is 2 pi. That means we can make this as cis 0 or cis 2 pi or cis 4 pi, cis 6 pi, and so on. But until where? Until when we have 6 values. So these values. And what do? You divide by 6. Okay, now we can find all the roots. Why? Because the first root will have modulus 1 with angle 0, so that's simply 1, right? And it makes perfect sense. If you put 1 there, 1 to 6 equals to 1. So this value is certainly a root. And the second root, we will have 1 times cis pi over 3, right? And that will yield 1 as well if you put it into this equation. And we can repeat this until the last root. So when we have the modulus 1 and the argument as 5 pi over 3. Okay, so this is how we can find the roots of unity. The a bit more complicated example is the second thing, where we have to find the roots when a complex number, when the equation is in this form. So not necessarily 1, but maybe another complex number. So I'll try 2 examples for this. So W must be a complex number, but we know that complex number can be just purely real or purely imaginary or purely, a combination of those two, right? So let's say, I'll try 3 cases. So when W is purely real and not 1. So we have already seen the case where W equals to 1, right? where we have to find the nth roots of unity. So let's do something else. So let's say, for example, z to the 5 equals to -6, let's say. Then we follow what we did just now. So first, let z be r cis theta. Then r cis theta to 5 will equal to -6, right? So r to 5 and cis 5 theta will equal to -6. So for this -6, why don't we write it as 6 times -1? The reason why I'm separating this negative sign is because I'm trying to put this -1, replace this -1 as in the form of polar form. Because for this 6, we can let that be r to 5, right? Because that's we can treat this as the modulus. And for this is where we apply this. So note that -1, it's cis pi. So that means we can write this as 6 times cis pi. So again, compare the values like this. So r to 5 will be 6. That means r will be 6 to 1/5. And cis 5 theta will be cis pi. That means 5 theta will be pi, but remember, note that this is to the 5. That means since the degree is 5, we have at most 5 roots. So 5, 3 pi, 5 pi, 7 pi, 9 pi. And the reason why we can use all these values is because this -1, we can write it as cis pi, but also cis 3 pi, and also cis 5 pi, cis 7 pi, and cis 9 pi using the period of trigonometric functions. Okay? So that means theta will be pi over 5, 3 pi over 5, pi, 7 pi over 5, 9 pi over 5. So we have the 5 roots. So the first root will be this, and all the way to the last root, which will be 9 pi over 5. This, okay? So not that difficult. One thing, in some questions, you will be asked to express your answers in Cartesian form. That means you just need to expand this out into Cartesian form. So cosine pi over 5 plus I sine pi over 5, and then you can use your calculator to find it, okay? Alright, then the second case, when w is purely imaginary. So what does that mean? Let's say z to the 7 equals to like 3i, okay? Then again, what's I? I is cis pi over 2, right? Then, so if we let z be r cis theta, r cis theta to 7 would be 3 times cis pi over 2, right? So r to 7 times cis 7 theta will be 3 times cis pi over 2. So r to 7 will be 3. And 7 theta, we have a lot of candidates. So there are 7 roots here, right? So that means pi over 2, 3 pi over, so it increases by 2 pi. So that means 5 pi over 2, and then 9 pi over 2. So you add up everything by 2 pi, okay? So these are the possible roots. So the first root, we can write it as, so r here is 3217, or like this. So modulus times the first angle, and second modulus times the second angle. Oh, wait, sorry. Remember that we have to divide every angle by 7 as well. Right, so the first one would be this, second one would be this, and all the way to the last root, which will be this. Okay, so again, it's not that difficult. So you see that the idea is the same. So you just try to make this into polar form, okay? So make this W into polar form, and also make this one as in polar form, okay? Just in case when you have negative I, so something like where W is purely imaginary but negative in front, well, it's the same. Just write negative I in polar form. So negative I in polar form, okay, one quick thing is that negative I, that means 0 minus I, right? So the modulus is still 1, right? And the argument is arctan negative 1 over 0, right? So negative infinity, so that's just simply this is negative pi over 2, okay? Which is the conjugate, right? Remember that for conjugate in polar form, we put negative sign in the angle, so that's why we have negative pi over 2, okay? If you don't want to use negative pi over 2, then what you can use is probably 3 pi over 2, okay? So that's what it is. And our last case, so when W is a combination of them, so let me think of a case. Any case like z to the 5 equals to, I just want to make in a very neat form, so 1 plus root 3i, let's say, okay? Alright, then what we can do is that, again, make this into polar form. So the modulus would be 2, right? And the argument would be root 3 over 1, which is pi over 3, right? Arctan root 3 is pi over 3, so we have c is pi over 3. And the job is done for you, so just solution, yeah, example and solution. So let z be r cis theta, and then r cis theta to 5 would equal to this. So r to 5 equals to 2, that means r is 2 to 1/5, and 5 theta equals to pi over 3, and what's the next one? You just add 2 pi, so this, and you add another 2 pi, so and we just need 5, right, because it's to the power 5. So the first root would be something like this. Oh no, cis. Oh, and we have, don't forget to divide the angle by 5. So cis pi over 15, and all the way until the last root, where it will become like this. Okay, so this is the first application of complex number that we can have. Alright, so the second example is something like trig identities with complex numbers. So you see that using polar form, we have a lot of trigonometric functions involved in complex numbers, right? So that means why don't we use some of the properties in polar form to derive some of the trigonometric identities? And these identities are not the ones that we learned in basic trigonometry that we learned, okay? So two main types of trigonometric identities we can have. So the first thing, okay, so this is the second example, so I'll call it A. So we can write multiple of theta in multiple of theta of sine or cosine into power of sine theta or cosine theta. So what does that mean? For example, if you have a multiple of theta like this, then you want to change this into an equation like this, cosine theta to n, okay? And the second case is the other way around. So when you have the power, then you change to multiple of theta. So for example, if you have sine theta to n, then you try to make it to sine n theta and so on. It doesn't necessarily mean that you'll have just one term for the conversion when converting. So you will have multiple terms, okay? So in order to do these examples, you need to recall one of the things that we've learned in the beginning. So these two. Why do you think we need this? Because note that if a complex number is in, for example, a polar form with modulus 1, then its conjugate would be cis minus theta, right? What do we have if we just want the real part? So remember, the real part of z is just basically adding the complex number with its conjugate and divide by 2, right? Because if you add these two and divide by 2, so you see that, remember, using just making this into Cartesian form, the sine part, the imaginary part would cancel each other, right? And you will just have 2 cosine theta over 2, which is cosine theta. And doing the similar thing for imaginary part, if we subtract them and divide by 2i, what we will have is that the real part will cancel, and you'll have a coefficient of sine with 2i. So if you divide by 2i, then you'll have this, right? So if we expand this using the theorem that we learned, so whenever I say theorem, I'm basically referring to the where is it? Sorry, I'm missing the paper. So the De Moivre's theorem. Well, I still can't really pronounce it properly. Oh, sorry, yeah, this one, this theorem, okay? So in Korea, we call it as Tumuruba theorem. I'll just use Tumuruba. So yeah, using that theorem, what we can have is that when we have expand this, oh, one thing, sorry. So z conjugate can also be written as z negative 1, right? Because z is cis theta, right? And using that theorem just now, if the power is negative 1, then we can put it to the as a coefficient of the angle, right? So that's cis minus theta. And using that, what we can have is that when we have this, we will then have 2 cosine n theta. Very easy to derive. So Zn, that means cis n theta. This will be cis minus n theta, and just expand it out, okay? And similarly, we have this, okay? Now, using this, what can we do? So I'll go for the first application where we have to change this to the power. So let's say show that cosine 5 theta equals to 16 one thing, so remember that in the previous video probably I have mentioned about whether you should use binomial expansion to solve the questions, and so far no, but for this one exclusively you need binomial expansion. So for those who don't really remember the binomial expansion, so when you have a binomial means two terms, right? Bi, two, and nomial, so like polynomial, right? So binomial, that means we have this, okay? And why do we need binomial expansion for this? Because from what we have seen just now, so that means, so this, we want to find cosine, we want to write cosine 5 theta as in the form of the powers of cosine, right? And we can find that cosine 5 theta would equal to z to the 5 plus z to the negative 5. So this, okay? But oh, sorry, 5. But for this one, it's not really good to use this formula because you have to expand two things, right? So why don't we just expand this? So what I'm trying to say is that you will still get the answer when you expand this out, but just expanding this, why can we just expand this, is because what is this? It's cis 5 theta, isn't it? That means cosine 5 theta plus I sine 5 theta. But we can also, this is from the theorem, right? But we could just directly expand this out using the binomial theorem. So that means cosine theta plus I sine theta to the 5. So cosine to the 5 plus sine squared I sine cube and I plus sorry, so it's 10, negative 10, and plus 5 cosine theta sine to the 4, and plus I sine to the 5. So some terms are purely real and some terms are imaginary, right? So what we can do is that we can write this in the form of Cartesian form. So real by real and imaginary by imaginary. So cosine to the 5, and this term, negative 10 cosine cube sine squared, and what else, this, plus 5 cosine theta sine to 4 would be the real term, and the imaginary term would be this with this and lastly this. Yeah. So this expansion would equal this, and this imaginary part would equal this, right? So that means cosine 5 theta equals to cosine to the 5 minus 10 times cosine cube times sine squared plus 5 cosine theta times sine to the 4. But do we see any sign in the question? No, that means we just need to convert all sine into cosine using the basic identity where sine squared plus cosine squared equals to 1. Therefore, sine squared equals to 1 minus cosine squared. So squared, that means cosine to the 5 minus 10 cosine cube plus 10 cosine to the 5, and plus, so that one we will have 5 cosine theta minus 2 cosine squared, so minus 10 cosine cube, and cosine to the 4 with this, so that's 5 cosine to the 4. So we see that that's 16 cosine to the 5, and then negative 20 cosine cube, and lastly we have 5 cosine theta. So that's the answer, right? One thing to tell you is that usually if you have a question like this in your final, you will probably have around 3 to 4 marks. That means you're expected to finish all this within 3 to 4 minutes. So is there any shortcut? No, this is the only method. And what you have to do is that you have to expand it out very quickly, and you have to rearrange it very quickly. So it's not really hard, but it takes a lot of time because there are many things to do. But again, it's not hard, so it's not supposed to be hard. So yeah, you will not have much time to solve this. So please try to do it as just try to finish it very quickly, okay? To save time. To finish within time. So that's the first example. Then for the second example is where we have to convert from power to multiple of theta. So let's try an example like show that. Alright, so as you can see, it doesn't necessarily, you will not have just single term. You will have a lot of terms when you change from one to another form, okay? So for this one, what you can do is that we're trying to use this time. And one thing, for this one, then do we not need binomial expansion? Unfortunately, you still need binomial expansion. And second thing is, then do we at least get more time than the previous example? And again, unfortunately, no. You'll have similar time, around 4 minutes as well. So again, whenever you see a question like this, what you can do is to just think, instantaneously come up with the way that you can solve, okay? And then quickly expand it out and then change in the form that the question wants. So for this one, then do we also directly expand that out, because we have cosine to the 6, and the answer is no, because for this one it's very hard to compare, right? So what we are going to do is that we are going to get the help from this. So remember that if z equals to cis theta, where the modulus is 1, then we have this formula, right? Then what we can do is that, solution. We can say cosine theta equals to half times z plus z to negative 1. Then if we want to find cosine to the 6, that means we just want to find this, right? So it's again binomial expansion, right? So you just solve it. So note that z to the 5, but we have z to negative 1, so that means z to 4. And 62 is 15, so that will be z this. And 61, 62, 63, and 60. Wait, is this 3? Oops, sorry. Z to the 6, and z to the 5 with z negative 2, and z to 3 with negative 3, so 15. And wait, what's wrong with my binomial? Oh, sorry, yeah, that's 20, sorry, 20. So yeah, I got a bit confused with the binomial coefficients. Yeah, sorry. So this is what you will expect to have. Huh? 4. Oops, I forgot one term. So z to 1, and z to negative 5, and lastly, so this is what we should expect to have. So I'm going to group it with the common coefficient. So this one we have z to the 4, and this one we have z to the negative 4, and this one we have z squared and with z to negative 2, and lastly just 20 as just as a constant term, okay? So this is what we have. And we use another equation. Remember this. So it's from this, right? We can quickly derive this using the theorem that we learned. So that will become 2 cosine 6 theta. That will become 12 cosine 4 theta. So 6 times 2, right? And that will become 3 times cosine 2 theta. And constant term is just constant term. So we will have, one thing. So when we make it to the 6, we have to make it to the 6 for this coefficient as well. So 1 over 64 times 2 times cosine, I'll just directly expand it out. So 1 over 32 cosine 6 theta, and that's 16 over 3 cosine 4 theta. So this is what we will have, okay? Why do we need this? I mean, and then can we do any further application? Well, we can. So for example, when you have to integrate this, then what you can do is that you can change into this multiple, and it's very easy to integrate this, right? So assuming that there's no coefficient, that's 1/6 sine 6 theta, and that's 1/4 sine 4 theta, and half sine 2 theta once you integrate it, okay? So yeah, you can directly use this result for integration, okay? So that's it for the complex number chapter. One more thing is that don't try to expect that the difficulty of the complex number questions in your final exam it's not like this. So this is the easiest examples that you will probably get. So I will post the sample test as well, and then I'll explain how we can solve those questions with some tips. So please go through the sample test or try some questions in the past paper, okay? So that's it for complex number. So see you guys in the next video. Bye.